Okay, let's get started. We're talking about heap and heap exploitation today. And last week we talked about Tcache, and the Tcache is used for small beans and fast beans, basically for those small chunks of memory, several bytes to several hundred bytes, not super big ones. And if you already have a malloc chunk, you have a malloc memory, you want to free that memory, this is how Tcache works. Some of piece of source code from the library, so that Tcache entry is placed exactly at the memory, the buffer. So it will not overlap with the previous size and the size, that header, okay? For that will be 8 bytes or 16 bytes for 32-bit or 64-bit systems. Then this is exactly how the C library, the Tcache version, put those free malloc chunks back to the bins. First, it will find the right bin it should be put back to based on the size. So this is just a simple calculation. The size -1 divided by 16, then you get to know which bin you are going to use. Then make sure the entry has not already been freed, so to prevent the double free. However, this is not a perfect solution. There are still ways to do double free, which we will talk about later in this class. So remember this free allocation, this location is the, what is this? That is the Tcache entries address or the buffer's address, okay? Then what is the free allocation 0? This here is 1. What is 0? It's the next pointer. Remember, that's the next pointer. So there are 2 pointers in the Tcache. One is the next, another one is called the key. Okay, so we're not changing 0 here. We're changing 1 first. We're changing the key pointer. We change the key pointer to the Tcache per thread structure. That's a global structure there. Okay, so that will be the key. So that's exactly what we saw here. So when we free entry A is inserted here, and we first change the key to this big structure, the global structure. Right? So after that, we will push that free allocation to the front of the list. So what we do is, so first, this memory malloc chunk, the next pointer points to the current head, okay? And the current head is at that global structures, that entry, the bin's first one, right? So that's the first step. The second step is we change that entry, the head pointer, to our current, the free allocation. Then we increase the count, because in global structure, we have a count to say how many available chunks are there in this bin. We increase that as well. Like I said, this is a singly linked list. So technically, if you traverse it, you get the count. You don't have to record that, but this makes sense faster. Then you also put the next pointer. So this is what we actually did before. This is for double free, but there are still ways to do double free. So if we want to do allocation, what we want to do is, whenever we want to do allocation, we first find a free chunk, okay? A freed chunk to do that. So even at the very beginning of malloc, the whole thing of that heap is a free chunk. That's called the wiredness chunk. Okay. So let's say first depending on how many bytes the program is requesting, we find the indexed. Then we check if for that size, we do have a available entry. If we do not have an available entry, we may go for a bigger bin, because a bigger bin can still be split into smaller memory chunks, or we can go to the wireless chunk to do that. Then we just reuse the allocation in the front of the list. So we are using the very first memory chunk available, which means this is a first in, last out data structure. It's kind of like a stack. Every time you put a freed memory chunk into a bin, then there will be more free chunks going in, and the first in, last out. So we can skip the steps. So we already did this. So the very last chunk, or it's also called the topmost chunk, the name of that is wideness chunk. So everything on heap at the beginning, you can consider it's just one huge chunk. It could be several megabytes or even bigger. So it's the top chunk. Then this top chunk basically borders the end of the heap. That is where the program break is. Okay, the break system call, the S break system call can change that. So the end of this wideness chunk is the border. Of course, there may be different threads. Then they have their own arena or their own heap. So this chunk actually follows the same format of the other chunks. That's why at the beginning you can think there is one chunk, and we're going to split that chunk into smaller ones to give us memory. If more size is required, then malloc library will use the S break system call to change the border of the last chunk. And for the wireless chunks, the previous in-use flag is always set. Its own itself is not used, but its previous one should always be in use. Okay. So a phenomenon we discovered of the current libc implementation is the first fit phenomenon. So basically, glibc uses the first fit algorithm to select a free chunk. If a chunk is free and not enough, so malloc will select this chunk to return. And this can be exploited in use after free situations. Let's say this is a program. At the beginning, we allocate two chunks. They are relatively big, okay? 512 in hex and 256 in hex. Then we get 2 pointers. Then we have another pointer. We're not allocating anything. Then we copy a string. This is A to the pointer A. So there is no buffer overflow here because this is big enough, and this is hard-coded string. So even though it's a string copy, there is no buffer overflow. Then we print out the address of A. Then we free A. So what will happen after we free A? So A will go back to Tcache, will go to the bins for the 512 one, right? Then we malloc 500, which is smaller than 512. Okay. So what will happen is the memory location we just returned, we just freed, will be returned to C. Okay. So here, after we free A, we didn't change A to 0. Okay. In say textbook, it is advised that after you free, you should change A to null or 0, right? But here we didn't do that. So A still has a value of that memory location, okay? Because we didn't modify A. Then C will have the same location. So A and C right now, they point to the same location. Okay. So if you print out the third allocation, then you will print out this is A. If you print out A again, it will also print out this is A. So here, this use, we print out A, this is called the use after free. Because you already freed what A points to, then you are still using the pointer A. Okay? You're not supposed to do that. You're supposed to change A to null. So if you dereference that, you can get an error at least. But here, that's a double free. Go ahead. So there are some smarter pointer or secure pointer solutions, but they're not necessarily at the inside of the free or equivalent functions. They may be at a higher layer to wrap that. That does make sense. There has been a lot of attempts to do that at the language level, but it may not make sense to do that in free function itself. Maybe it should be outside of that. So let's look at this once again. So at the very beginning, we do not have any, we didn't use any malloc yet, right? So everything is actually in the wiredness chunk. However, the wiredness chunk, it doesn't belong to any bin. That's why we do not say it in the T-thread global structure. So first we do a malloc A, we malloc this, then we have split this malloc chunk from the topmost chunk, okay? And this one is in use. That's why we have data here, okay? We put there is A in this one. Then we malloc again to get B. Then we have another malloc chunk for B. Then we free A. So when we free A, we're going to put this malloc chunk back to this bin. Oh, here is a typo. So here should be null. Then should be this one, should be A. Then A doesn't have a link to any other. That's why the next pointer is 0. The key is been there. Here is a typo. Right? So this is what we have. Then when we do malloc C, this is actually malloc C. The third time we malloc this, we're asking for yeah, this one also works. Let's say we ask for a much smaller memory, and one malloc will do it will split this into 2 malloc chunks, and return this second one to a smaller bin, and this one will be used as the say pointer as we showed before. There are some errors in my slides I need to change, but you get the idea, right? So that is called the first fit. Okay. Another example. Here we are using the same size, just a simple exercise here. We're doing 4 mallocs, malloc 20, 20, 20, 20, A, B, C, D. Then we free A, B, C, D. And this is the address of each malloc. So after that, we're going to do 4 mallocs again. So can you predict the address for each of them? Yes, exactly. It should be opposite because this is first in, last out, or last in, first out. So this one will go back to the free list, and it will be allocated again, okay? So it will be 9980, then go down that. It will be opposite. Yeah, it will be like this. Okay, next, let's talk about, yeah, go ahead.
So if it's smaller, what is the smaller thing?
Split into, well, first of all, it will try to find the best size it can, if let's say we have, you're asking for 256 bytes, then for the bin for 86 bytes, there may be already a free one. Then you don't need to split a 512 one.
What if it's like bigger?
You may split, yeah.
So like, we have like 256 bytes in cache.
Yes.
We model like 500 phone.
Okay.
Then like,
So you don't have a free 512 one. Then you split from the wiredness chunk, the topmost chunk, yeah.
why is it splitting from 500 bytes because the developer asked for 500 bytes, so it's just get a new bin.
It doesn't, well, I think the design of this is they do not want to ask for new memory when there are something available to keep the whole size small. Yes, so there is no absolute right or wrong here, and this thing changes constantly. 5 years from now, we will not know what kind of implementation they have. But right now, this is an implementation, and they believe right now this is a good implementation, fast and secure. Yeah. A lot of this depends on the upper layer applications. Your upper layer application, let's say it's a web server, and the packets you're getting from web server sometimes are just hundreds of bytes. That's why sometimes the package are small, and every time there's a package, you malloc that, you analyze that, and the Tcache is trying to accommodate those kind of things because we have so many smaller memory requests. Yeah. The next we talk about heap exploitation. This is another beast. A lot of ways to attack this, and things changes very fast. We will talk about several classic attacks here. So first of all, we can still do some kind of overflow, buffer overflow, if there is a buffer overflow vulnerability. And this is almost the same as a stack-based one. It's just we're not necessarily overwriting the return address. Sometimes we don't have the return address to overwrite, but we do have all kinds of complicated structures on the heap, okay? And those structures may have pointers, function pointers. And if you overwrite a function pointer, which is a code pointer, then you trigger that function, then you can run arbitrary code. Right? So this is our first example. We have a data structure airplane. Airplane has a function pointer. Then it has just a array of the characters, 20 bytes. And there is a function called fly. This is an airplane. So at the beginning of this program, we print out where fly is and also where print flag is. So print flag is in the address space. So we first malloc an airplane on the heap, and we tell you where the airplane 1 is. So we malloc another airplane, we call it airplane 2. And we have 2 pointers for it, P1 and P2, points to both structures on the heap. Then for the code pointer for both of them, we assign fly to them, okay? Then we want to get the name for those airplanes. So at the beginning, we don't have any malloc chunk there, or just the topmost chunk. So P1 is the first one, so it will have a lower address, right? P2 is the second one, so it has a higher address. Then we get the name of P2 first, then we get the name of P1, and here is a buffer overflow, and we're getting the name of that, and we're getting 100 bytes. Okay. So we talked about the size of this before. So after that, we just call the function with a function pointer, then we free that. Okay. The problem here is, here we have a buffer overflow, the overflow is not on the heap, not on the stack, but on the heap, right? So we talk about how big this is. So for 64-bit machine, the alignment is 16 bytes, right? So the whole structure, including the headers, at least will be 32 bytes or 48 bytes, right? So if we draw that, we'll have something like this. So airplane 1, we don't really know which address this is, okay? And it doesn't matter. What we know is airplane 1, it will return this place, the buffer or memory, but it has a 16 bytes header. The header has two parts, the previous size and the size, okay? Then it has the function pointer, because function pointer is the first member. Then we have name, put in, okay? So the whole thing will be, so here we already have 16, 24, and we're asking for 20 bytes of this. So this has to be at least 20 bytes. So in total, the whole thing will be 48 bytes, which means the name here we get is actually 24 bytes. Then we have airplane 2, the same structure. And we said before, because it's T-cache, the precise part is not really used. So in this case, the name part actually you can up to 32 bytes. But whatever, here, the override is 100 bytes. So we will be able to overwrite from this place, go up to the whole thing of airplane 2, actually, right? So by overwriting this function pointer, then later, when the P2 function pointer is called, we can ask it to call any function, right? So the goal of this challenge is to overwrite this to the print flag function. So when this one is called, you capture the flag, okay? So that's the idea of that. And I will leave you to that later. So, yeah.
If you override like 100 bytes, then we go above the name of everything, but that is not malloc. Get an error or it will.
So what is after this? That's the topmost chunk, right? It's still on the heap. And it will be much bigger than 100 bytes. So you will not be able to override something significant.
But we will not get an error.
You will not get an error. Yeah. There's no such thing as calorie or whatever here. Yeah, you're not getting an error. Yeah. But if you are overwriting the header of that, the wiredness chunk, if the program later do another malloc, there could be error. Yes. Yeah. Okay, I will leave this to you later. I'm trying to do less demo in the class now. So then I'm going to walk around to help you get this, because at this moment, I believe you are able to solve those challenges. Yeah. So instead of giving you directly the exploit, I want you to do that. Okay. So that's overflow. The second class of vulnerability we see a lot is use after free vulnerability, UAF. This is a class of vulnerability where data on the heap is freed, but a leftover reference or pointer, usually we call it a diagonal pointer, is used by the code as if the data were still there, still valid. So the term used after free actually can be more general. It can cover other cases, not only this attack on the heap, right? Last week, I think I sent you guys an invite. There was a speaker from Stony Brook, and he works on web stuff, and not only just browser stuff, but web stuff. They have been working on all kinds of use after free problems, diagonal pointers of the domain names. So imagine you have web page, and the web page will request all kinds of resources from other websites, like JavaScript, like HTML page, right? And many websites, the web pages, they rely on the libraries from other places. They request our JavaScript from other places. But the JavaScript they are requesting from may expire because you're asking JavaScript from a third party. There's no guarantee 2 years later that third party is still there. They may not be there anymore, right? So then the JavaScript, the script tag in your HTML, that's actually a pointer. Not at this level. It doesn't point to a memory location. It points to another piece of JavaScript provided by third party. That's still a pointer, right? So when that pointer, when the resources it points to doesn't exist anymore, okay, the attackers can register that domain and host a malicious JavaScript at that URL, and it will be retrieved by your web page, and your web page will present that to your users, right? So that's also a use after free case, obviously not at this layer, not at this scale, right? It's also called the dangling pointer problem. Yeah. So for complex binary programs like web browsers, you have multiple threads, thousands of threads, and each thread is requesting some resources, and sometimes one thread will somehow abort. Then some resources will be leaked. There will be all kinds of weird situations, and use after free may happen. We saw an example just now, that's a use after free. So more concrete example here. So left-hand side, we have the memory map. Right-hand side, we have just the heap. Okay, so this is the rooming of the heap part. Then we may have a pointer. The pointer may be in the data section, maybe on heap, or maybe on stack. The pointer first points to some data on the heap. Then we freed this data, and we put some new data there, right? We freed it, then we put some new data there. The new data has a totally different structure, okay? As we saw just now. No, the example we saw just now, we use the same architecture, right? The same structure, airplane, but it could be a different structure because when you malloc something, you don't care about the semantics of that object you're mallocing. You only care about the size. Malloc only cares about the size. So you may allocate a different object, different structure, just the similar size, smaller size. Then you may use the pointer in a wrong way. The correct way to do this is you should, like I said, you should set the dangling pointer always to 0. But this is software developers' job, and developers make all kinds of mistakes, right? And that's why some languages provide smarter pointers to solve this problem. Yeah. So how do we exploit this? Usually, we allocate a different type of object, and we can exploit this. So we change this example a little bit, the previous example a little bit. This is a heap UAF1. Let's do 32-bit for this one. It also works for 64-bit. So we have two structures here. The first one is an airplane. The second one is a car. They have the same size. Both of them has a name and and another member. So they are the same size. Okay. But for airplane, there is a function pointer. For car, there is just a volume. Okay, the engine volume. This is before EVs. Okay. So first, we print out flight's address and print flag's address. We have print flag here. We malloc the airplane. We set airplane to fly. Then we call the function, so it will fly, saying it will say flying. Then we free this one. Okay, but we didn't set this to 0. We have a dangling pointer here. Then we malloc a car. And because the first in, last out, this car will actually have the same address as the previous airplane. So P and P1, they will have the same address, right? But here, because this is car, it doesn't have that function pointer, it doesn't have fly, it has a volume. Then it asks you to input the volume, okay? Then you input the volume, put the volume there. Then here's a mistake here. There is a use after free. Instead of doing P1, if we do P1 pointer pfunc, this will not work, right? The C programming language will capture, this is an error, the pointer P1, which has a type of star car, doesn't have this member function. Okay? But instead, we're doing P, and P is pointed to the same address. And P has this function, and we're calling it a function. Okay. Then you can say to capture the flag here, you need to get the address of print flag and input that as the volume for the car. Then later, it will be used as a function pointer to trigger that. So you can capture the flag. Make sense? Yeah. Okay. So this is the first version of this. This is the second version. Slightly different. Make it easier, we are also doing 32-bit. We have the, this one we need to do 32-bit because I designed it that way. Okay. Car have the same size, 20 bytes. However, the volume here is 8 bytes in a 32-bit machine, and the name is only 16 bytes, okay? This is one of the final challenges I gave to the students several years ago. Yeah. Then here, you're not inputting the previous volume, 4 bytes. You are inputting 8 bytes of volume here. Okay. But only 4 bytes of that will be used, not all the full 8 bytes. Only 4 bytes of that will be used as a function pointer. So what kind of input you should put here to make it call the function print flag. Obviously, what important here is let me see, is the least significant 4 bytes. The higher 4 bytes part doesn't matter, but you can only input 8 bytes in total. You can only input a huge number to get, in one shot, you can input that. You cannot only input the least significant 4 bytes there. Yeah. So we will do this later. You will do this later. Okay, then we have several other challenges, but I forgot to put those on the server. I will put them on the server later. All of those are from Sharefish, so how to heap tutorial. So Sharefish is one of the best hacking teams, college hacking teams out there. They're from Arizona State. So this one we are going to, in this example, we will show double free. So there is a freed memory, we freed twice. Okay. So at the beginning, we have 8 pointers. We malloc 8 bytes and 8 times. Okay. Then we free them. So here we have 7, but 7, 8 doesn't really matter that much here. Then we freeze it. So what happened is there will a bin. That bin is for 8 bytes of memory chunks. Okay. Actually, maybe bigger than that, right? So for 64-bit, actually, the bin will be for 32 bytes because 18 bytes of metadata you ask for 8 bytes, then 8 padding, so 32 bytes. Okay. Anyway, there will be bin for that. Then in that bin, we free all of those. So we will have, in this case, we're freeing 7. Okay, we will have 7 members in that list, 7 items in that list. Then we do malloc again. In this case, we're not doing malloc or doing calloc, but the same thing. Well, one item, 8 bytes, so still 8 bytes. So we're still using the same, reusing the same memory. We calloc 3 times. Then we free A again, so that A will go back to the list. We free B, B will go back to the list, and B will be the top, A will be the next. Okay. Then we free A again. Okay. So what will happen with free A again? So the current implementation cannot detect this is a double free actually. But what will happen is when we free A again? What will happen to that B? So the head will point to A will point to B will point to A again, right? So that will happen. Yeah. Yeah, I don't have an animation here. So the head will point to A will point to B will point to A again, and A points to now there, right? This is what will happen. Then we allocate again. We allocate A, B, C. So this A will be moved out and will be A, and B will be moved out, will be B, and C will use this one, right? Then A and C will actually point to the same address. Okay. So if A and C, they are different objects, like the previous example, then you may trigger some kind of error, right? So this is the results on my laptop. I will put this on the server later. So we first allocate 3 buffers. Before that, we already have some freed ones there. Then the first allocation will get this address, 3A0, A0, C0, E0, as expected. Then we free the first one. So after we free the first one, we actually, after that, we free the second one again, then we free the first one again. So the free list has A0, C0, and A0, okay? Then we do 3 allocations. The first one will be A0, the second one will be C0, the third one will also be A0. That is not supposed to happen, okay? Because of the double free attack, we tricked malloc to return the same malloc chunk twice to the program. Okay, so there are 2 pointers pointed to the same memory location. So if one is controlled by the attacker, another is controlled by the victim, the attacker can directly change the victim's memory content. So we can actually trick malloc to return memories that are not even on the stack, are not even on the heap. It can be on the stack or other locations. Okay. So at the beginning, the same. We have some, we malloc some, we free all of them. Then, so here, the whole thing is in a function. Then we have a stack variable, a local variable, the unsigned long, full of unsigned long. In this case, let's say unsigned long is 8 bytes. So the whole thing is 32 bytes, okay? So why do we choose 32 bytes? That's the size of a malloc chunk of this, right? If you malloc chunk your malloc 8, the malloc chunk size is 32 bytes, right? So here, we create a local object, local variable, and its size is 32 bytes. We make it align to this address because a malloc will allocate, will do a simple check to see if it is aligned. Then we are going to allocate 3 ABC like that. Then with 3A, 3B, 3A again, okay? So A, now we're getting here again. A, B, C. okay? But right now, all of them points to the heap. Now we allocate D again. So now we change the header points to D. D points to A. Yes. Then we're going to set this variable stack bar. So this is a stack bar. This is a local variable. Each of them is 8 bytes. So we're going to forge. We're trying to forge a fake memory chunk on the stack. Okay. So what should we put here? What is this field? Remember, previous size, right? This is previous size. Okay. So the value doesn't really matter. What is this one? This is the size, right? Okay. The size is the whole data structure size. What's the size? 32 bytes, right? Which is 20 in hex. Okay. That's why we put 20 in hex here. Okay. Then we put, so what's this one? This is next. Next one we have we points to stack bar. We actually points to here. Then this address we unsigned long address. This one we put this address here. No, this one is different one. No, those two are not here. Those are two. This one is not here. Not the next one. So pointer points to here. Pointer points to here. The address is this address. Then we dereference this address. Okay. So what is D? D is a free chunk here. And we have the pointer. We're going to change the heap here, right? We're going to change the heap, and we are changing the where's D? What? This address. D is what? B's address? Allocate. Oh yeah, made a mistake here. Here, D is not there. The D is a malloc. The D is so we have okay. Yeah, here is wrong. This one is wrong. So after we do free A, free B, free C, free A again. Okay, it should be this. With free A, with free B, with free A again. Right? This is what the bin looks like. Then we are doing a malloc. So we're doing a malloc, malloc D actually. Yeah. Right? Malloc D. Then the bin will look like, because we do a malloc, so this one will not be in the bin anymore. We'll have a B, and we'll have an A, then here, right? Okay, it will look like this. So then D, so let's say this is A. This is A. A has previous size, then should be data in this case. But if it's freed, this will be next and key. Okay. So now D and A, they point to the same location. They all point to this location. No, sorry. It actually points to here. It points to here. Okay, does this make sense? Okay. Now we are going to, then we have another stack variable, which is this. This is a stack variable. And here we set 20. Then pointer points to the stack variable, address is D. Then we dereference this address. So this address so what are we trying to do here? This is D points to this, and D, what's the size of D? It's just unsigned long. So we are trying to change this field, right? We are trying to change it to address, right shift 12 bytes, then with PTR, inclusive all with PTR. I kind of forgot what's going on here. Let's see what's going on here. That address. Yeah, I'm trying to figure out why we're doing that. So how big is this one? 8 bytes, right? Yeah, this is 8 bytes, which is 64 bits, right? 64 bits, and we shift 12. Let me see here. Yeah, go ahead.
It's different like image of like this
Mhm.
to like remove the address to like right. So you can like speak it later.
Yeah, but then why we're doing exclusive OR here? PTR. So the goal here is to point the next one to the stack, right? To here. That's a goal, right? So because this is A, so it's from here you can say A is still free. So it can be allocated again, right? Then A here is supposed to, the next for A is supposed to be no, there should be no others. What we're trying to do is we're trying to change this one, change this to the stack var, right? Stack variable. So when we allocate B, when we allocate one more, we're going to allocate for this stack variable, okay, which is not even on a heap. But malloc will believe that this one is a free malloc chunk, but actually it's not. It's actually on the stack, right? So what we're trying to do here is to change this pointer. What we're doing is we shift 12 bits, then do an exclusive OR with the PTR. How did we get that? So why this address equals to this? Because PTR, what is PTR?
In the first bin diagram.
Huh?
In the first bin layout.
Yes.
Like, both of the A's are the same or like they're different.
They're the same. Yeah. The A here means a pointer. They point to the same thing. Yes. So this is a double free. So here, free A, free A. This is a double free. Double free.
Like a cycle of A point to B.
No, this is just a singly linked list. So A, the next points to B, B points to A, and you mean here should be B, right? Oh yeah, in this case.
When
Yeah, so technically this looks like a cycle. Yeah, or underness list here because they point to the same thing. Yes. Yes, you're correct there. Then what we're doing is we're still trying to, so for A, so here is supposed to change to link to B, but we're going to change that. Instead of next is B, we're going to point to stack far, right? So the PTR is the first one. Oh, PTR is this one. Okay. That's starting to make sense because the address we want to get is this one points to. The PTR actually points to here, right? PTR, not here. So this is just the name of that. This is just the name of that. PTR points to the if we think this is a malloc chunk, pins to the previous size. But the actual address we're trying to get is here. Okay. So by shifting 12, we are oh yeah, stuff makes sense. We are doing this is a right shift. So in C, this is shift to left or right. I mean, this is shift to higher or lower? I think this shift to higher, right? Okay, yeah, this shift to higher, that makes sense. Okay. So what's going on here is after we shift this to higher 12 bits, then the least significant 12 bits will be what? Will be 0, right? Then 0 exclusive OR with anything will be that thing, right? 0 exclusive with 1 will be 1, 0 exclusive OR with 0 will still be 0, right? Which means we keep the least significant 18 points there. 18 bits, 12 bits there. Is
height should actually move like that.
move to small lower. Okay, so it should.
I think he is the target.
So 12 bits of the pointer is the 12 bits of address. Okay, the least given 12 bits is discarded. Then why do we do exclusive OR with PTR? Okay, I'm a little bit confused here right now. Let's take a look at this result first, and that may help us explain. I think I probably missed a malloc there. When I clean up the code, I probably delete something by mistake. Okay, let's say. First, we have a stack variable, right? Look at this address, 7F. This is a stack variable. This variable, and we want the malloc or calloc to return this. Okay, we want to trick malloc to do that. Malloc is not supposed to do that. We allocate 3 buffers. They all have this 56 address, 80, A0, C0. Okay, then we free ABA. Then the free list have 80, A0, 80, and like you said, the 80 actually here, yeah, the 80 here actually may point to A0 again, right? Then we do 2 malloc, 80, A0, that makes sense. Then the free list will only have 80, will only have A, okay? We only have A. Yeah, this one, 80. That makes sense. Now we're trying to write a fake size 20 to the stack, and we point that A. The goal is to point that A. Here, this is still our goal. We don't have this one anymore, right? The goal is to point A to the stack variable. So it will look like something like this. So we overwrite the first 8 bytes of the data at this to point right before this. So 8 bytes of A overwrite, yeah, this to this. Okay, so it's correct. We understand correctly what it is trying to do. It's just that a shift is a little bit confusing there. We need to dig into that, how that shift works. So after that, we do 2 more mallocs, right? Now the free list looks like this. Then we do a malloc. This A will be reused. Then we do another malloc. The stack variable will be used as a malloc chunk. Okay. So this is the goal of this, is to trick malloc to return memory on stack. And obviously, this can be anywhere, not just the stack. Okay.
For printing the previous address to you.
This free one? The program here to print the free is not do a traverse of everything. Yeah. Yes, manually print that if you look at the source code. Yeah.
You don't know if there is cycle. I don't think there is cycle. You cannot validate that.
It will be a cycle actually. Yes. It will be forever there. Yeah. Okay. That makes sense, right? So I need to figure out how that shift works later. Yeah. So this is double free. So now you can see that with double free, we can get 2 pointers point to the same malloc chunk. We can also trick malloc to return something that is not really on the heap. Then this can be combined with stack-based buffer overflow. You trick malloc to return something on stack, which you can overflow, you can change, right? Something like that. Yeah. So by combining them together, you can do something very complicated. Okay. Then for other bigger chunks, not fast beans, so Tcache will split a malloc chunk to smaller malloc chunks. But Tcache will not merge 2 adjacent malloc chunks to a bigger one. But if your memory size is bigger or it's not using Tcache, the implementation of malloc may choose to merge two chunks together to form a bigger chunk. And when we do that, we're not using singly linked list. So Tcache use singly linked list. So the two fields we have is next and key. For bigger ones, or if we are not using Tcache, the data structure is different. The data structure is we have this data structure, which is a doubly linked list. We have a forward link to point to the next malloc chunk, and a backward pointer to point to the previous malloc chunk. Okay, so this is double linked. Yeah.
So it's the sign like it's like the forward and side and backward and side.
This one?
Yeah.
Only for very large ones. Yes, for free ones, very large ones, they're actually used. Yeah. That's why it's very complicated stuff. Yeah. Go ahead.
We request malloc just for 4 bytes. So it will have 2 bytes of previous side and current side. 4 bytes of that, and then 4 bytes of this side.
You are talking about without Tcache?
It-
With Tcache, the previous size is not used.
But it will still be the 8 bytes for that.
Yes, it will be still 4 bytes on 32-bit machine. Yes.
So the total will be 32 bytes. So chunk will be-
The chunk will be how many bytes you are requesting? You are requesting 16 bytes on a 30.
4 bytes, the chunk will be-
Oh, you are requesting 4 bytes memory from a 32-bit machine. 32-bit machine, the alignment could be 16 bytes. Then in that case, 8 bytes. Yeah, say 16 bytes will be enough. Yeah.
Whenever we see, we will have this next thing. What is the minimum, like, if something is free, and it will be 32 bytes long.
Yes, exactly. Yeah. So malloc may choose to merge them. Let's say we have, so this one, this is lower memory, this is higher memory. We have 3 chunks here, chunk A, chunk B, chunk C, and B is already freed. C is allocated, A is being freeing. So B has previous size, and the size part, 1 bit saying previous one in use because we're trying to free A, right? And B is already freed. So it has forward pointer and backward pointer here, okay? And this one is not in Tcache. That's why this one is not next or key, okay? Instead it's forward and backward. Then A is what we're trying to free. And depending on the implementation, when A is freed, malloc could merge those 2 chunks together, okay? Merge them together. But Tcache is not doing this, okay? Tcache is not going to merge them. Tcache will keep the size. The reason Tcache is doing that is Tcache is trying to serve smaller memory requests. Like the use case here is there are a lot of small memory requests, and the Tcache is not wasting time to merging memory chunks to larger ones, but instead of keeping them small. Okay. So to merge this, what happens is we are going to. So let's look at this. So this is a bin. We have 3 chunks, 1, 2, 3. The bin, the head, it's actually either way is fine. And we go this way maybe. Yeah, because this one is freed first, this runs first second, this runs first third. Okay. So the head will point to the last freed one. So the head pointer will point to chunk 3. Chunk 3's forward pointer to point to chunk B. Chunk B's forward pointer to chunk A. Then go back to the bin itself. So this is a double linked list, right? It's double linked.
Why does chunk 1 go to there?
What?
Chunk 1 is the last one where the last thing equals to
Point to null.
the
In this case, it's this is doubly linked, and then try to make it a circular link. Yeah. The benefit of doing this is you can, from any place, you can quickly find another place. If you change this to null, then you miss the opportunity to find at the end, right? Because the head here is also the tail. And this is a pointer, global pointer you can always have. So you can search from the head or search from the tail directly. Well, this is a usernet thing. So technically, you can choose whatever you want. You can run a program and say, I'm going to use a different version of libc. I can use my own version of libc. Yeah, it's just different version, have different implementation. But when you run the program, you can choose what to use. Yeah. So we're looking at the default version. When all the programs, when we run, we didn't specify which library to use, right? We're using the default one. Okay, so there is an unlink function or macro in the C library to free a chunk, to unlink a free chunk from the bin. So when we say unlink a free chunk from a bin, it could be that chunk is being allocated, right? It also could be that chunk is being merged into the previous chunk. Okay. But anyway, we're removing that one from a bin, and bin is only for free malloc chunks. Okay. So, and this is not Tcache. So before we unlink this, looks like this. We have, this is low, that's high. We have chunk 1, then we have chunk P, we have chunk 3 here. Okay, so chunk P is what we're going to unlink. We're going to use this one. So chunk 1, the forward link, there may be other chunks in middle of them, obviously, but those chunks may be in use, right? So they are not really in the bin. Okay. So here I only draw those three in the bin. Others, there are many. They may be in use. They're not freed ones. Okay. So chunk A's forward pointer points to chunk P. Okay. Chunk A's backward pointer, in this case, we don't really care, so I didn't put it there. Then chunk P forward pointer points to chunk 3. And chunk P's backward pointer points to chunk 1. Okay. And in this case, we are pointing to the beginning. We're not pointing to the pointer. Okay. Then chunk 3's forward pointer will point to another one, which we're not showing here. But chunk 3's backward pointer will point to chunk B. Okay. So this is the structure. And in C libraries, this is a macro. The macro to unlink this. And let's say what kind of problem we could have here. So in this macro, we're trying to unlink P. We're trying to remove P from this link, from this list. First, we have we can say a local variable, a temp variable called backward. We set backward as P's backward, okay? Which means backward will point to here, okay? Then we put forward as P's forward, then forward will points to chunk 3, backward will point to chunk 1. Then forwards backward will be set as backward, which means chunk 3's backward will go to chunk 1. Then backwards forward will be set as forward, which means chunk 1's forward will change to chunk 3, okay? Then this chunk is not in the list anymore. Make sense? Right? Okay. So this is a macro. Looks like it's correct, right? The problem of this is this can be used for an arbitrary memory write, because you are, as attacker, let's say, as attacker, we are controlling chunk P. This is what we control. Because we control chunk P, we can control everything here. We can control the backward and we can control the forward. Okay. And if we control that, then we trigger an unlink. So the forward will not point to a real chunk. The backward will not point to a real chunk. It points to some other location, memory location. Right? Then, if we can trick malloc to unlink this chunk, then malloc is going to overwrite some offset from BK, the backward, and some offset from the forward. And if we control those two, then we can ask malloc to write other locations. They're not necessarily locations on the heap. The problem here is you do not necessarily can overwrite arbitrary value to arbitrary address you are trying to overwrite. Right? So it's a limited attack, but very, very complicated stuff. Yeah. So also, to really understand how to attack this, you need to understand every bit of how the heap works, and it changes very often. The free algorithm, the code may also have some other bugs as well. Let's say this is another case. So you can see this is from a very old book, actually. We have chunk A in use, chunk B also in use, and the bit of chunk B in use says previous chunk in use is set, which means A is in use. This is before overflow. Now we can overwrite, let's say here we can overwrite A and B. So we can fake data in that address. We're trying to, this is like our first example. We have an overflow, heap-based overflow. We can overflow from here. Then from here, we can overwrite things. But instead of overwrite a function pointer, we're trying to create fake chunks at those locations. We can also forge fake malloc chunks at other locations, as long as you can trigger. We have a fake ones. We may need to trigger a free, like what we did in a double free one. Okay, let's say here we have two fake chunks. The first one we have a size of itself, a forward one, a backward one, and this one we pretend this one is not really in use. The second one also not in use, so we have forward and backward. Then we have previous size of this one and the size of itself. Then when we free A, malloc may realize that the next chunk is also a freed one. this is not Tcache. Then malloc will try to merge them. Okay. Right? Malloc is trying to merge both chunks into a bigger chunk. Okay. The whole thing will become one bigger chunk. But to merge them, malloc believes those two are already in some bin, right? Then we want to unlink them from existing bins, because malloc believes they are free ones, even though they are fake ones. And it will call the unlink macro we just saw, macro. And everything here we can forge. Then we can use this to do a arbitrary override to the location we want to overwrite. We may not be able to override. I think for some field we can override. Oh yes, for some field, for those two fields we can override arbitrary value actually. Right? Yes. No, we cannot. It's complicated. It's not really arbitrary value because it's first used here, but we can change the value. For example, if the value used to be 0, we can change to non-zero. If it's authenticator global variable we saw before, it's good enough. Yeah, go ahead.
The first data inside like left that is before, right?
Data left?
So let's say we model we free like there's two chunks.
Yes.
When these two chunks are being merged,
Yes.
like entire data, unless I do like say, like fill 0, it's just like every data from like previous.
It's still a freed chunk. It's just a bigger freed chunk.
Okay.
Yes. Yeah. Yeah. So heap is really complicated stuff, as you can sense. I took a lot of materials from those resources. So if you are into this, actually, I also need to explore more about heap, especially at the kernel level. So I think the first two, maybe the very early version of heap, first three maybe, the very early versions of heap exploitation. Then there are some more modern ones, like this one, Sharefish one. It's quite modern. They analyze the most say library versions, and some bugs are fixed. Then there are new bugs, and they have different examples there, and also they link to real-world CTFs. Those are CTF challenges. Belongs to this kind of vulnerability. The link to that, you can try that. And also there is a simple tutorial by this guy. But this one is not. This one is a little bit. It's a short tutorial. Most of the things you can find on Sharefish actually. Then also there are research projects. Also attack tools, especially based on Anger. There is a heap helper to do automated heap security analysis. Yeah, those are where you can also publish papers. Any questions? That's for all for our heap. I will give you more. I will give you some homework next week on a heap. But what you can start doing now is at least those overwrite ones, which I give in the final exam before. Yeah. Also, this week's homework will be. I already put the homework online. The homework of this week will be ROP. Some of you already finished maybe 1 or 2 of them. There are 4. And I guess this one will be a little bit trickier than last week's homework. So if you need office hour, just ping me on Slack anytime, then we can schedule time to discuss this. Cool. Any questions about heap or? Okay. So if there is no other questions, next Thursday, we're going to talk about cache side channel attack. So 15 years ago, people wouldn't consider cache side channel attack as part of memory corruption attacks. But now the boundary of them is very blurry. You can use cache-based attacks to help memory corruption attacks, and sometimes can directly use cache side channel attacks to change memory, or not necessarily cache side channel, but other side channel. Like there is a row hammer attack that you can just flip the value of some memory, like DRAM rows. Okay, for example, the row of that DRAM is just set, it's all 1. Then you change all of them to 0. Okay, flip that. Okay. And this kind of flip you can trigger at a very high level. You can even trigger this in JavaScript. Right? JavaScript eventually will be executed on your CPU, on your memory, and you change the variables of JavaScript, you can flip some row of memory, DRAM. And if you flip one row and you flip really quick many times, and you may influence adjacent rows. Imagine you have a big variable array, and there is another local variable kind of like authenticated. It will be 0 or non-0. If you change your array's value, okay, then your authenticated, the variable's value will also be changed. This is not at the programming language level. The programming language didn't do anything wrong. This is not even at the binary level. This is only at the memory level. This is called the row hammer attack. So it's because at the circuit level, if you switch the capacitors really quick and long enough, it will influence other capacitors. And the memories are basically each cell is one capacitor and resistant, right? Yeah. So so those kind of attacks right now are also very real. And 15 years ago, no one think about them as memory corruption attacks, but now you can see they are also related to memory. So we're going to talk about those attacks, especially focusing on cache. I have some experience on cache before, did some projects in cache, both attack and defense. Okay, then after that, we have one more class. We probably also need to cover cache. And also there is a keynote speech I really want everyone to watch, so we can maybe watch that together. So that keynote speech is from CCS several years ago. That keynote speech advocates us to use Rust instead of memory unsafe languages and C and C++. Okay. And this year, maybe early this year, the White House also have an, I don't know, is that a suggestion or executive order or something, talking about in the next few years, we need to switch to memory safe languages like Rust, okay? Which means the software security class like this will also need to change significantly because 15 years from now, those attacks may not work anymore, right? Yeah, if we all switch to Rust. But it's not easy to switch to Rust. First of all, Rust is not really a language easy to program. Okay, a lot of constraints. The reason it's safe is because it has a lot of constraints and make it harder to programs to master that. That's why also I'm thinking about a research project is try to use large language models to translate from C to Rust automatically, especially on the systems I'm interested, like firmware stuff, low-level stuff. But low-level stuff is hard to translate because they need to do a lot of memory management directly. There were raw pointers everywhere. So how do you translate those security? If you translate Rust C to unsafe Rust, then it doesn't really change things. It's still unsafe. It has to be safe Rust. We'll actually also have a paper talking about this, which we get some positive results yesterday. It's not accepted yet, but some positive feedback yesterday is talking about we talk about why it's difficult to program embedded systems using Rust. That's part of the story of that paper. Yeah. Because you have to do a lot of raw pointers at that level. And when you do that, even if you are using unsafe Rust, it's not safe. Okay, we still have like we still have like 20 minutes, maybe 15 minutes. So you can either do the homework or work on the challenges we talked about today. Those challenges will be I think next week's homework or the week after.